So what I want to start with is reviewing what we know about maxima and minima problems from Calc 1. So in Calc 1, well, first of all, we had a lot of terminology that we introduced. So what it means to be a local min or max versus what it means to be an absolute min or max. So local min or maxes are places on the function where the neighboring points so for a local min, let's maybe it's easier to draw a quick sketch of it. Right? Local min is something that perhaps if we did that, I'll use a different color for that. Say that, right? Then then this point right here is a local min, but it's not an absolute min because, as you can see, the function will go off to minus infinity. And same with this point up here. This is a local max, but not a global max because the function, this cubic, I'm trying to do a cubic, it extends infinitely in both of those directions. So these 2 points in red are local min and max because the values that are immediately surrounding the point, if you make a small neighborhood around the point, they have the correct property of either the point is higher than all the others, meaning it's a max, or that all the surrounding point, the way I worded it is kind of backwards from what I was saying. So the point is lower than all the other points around it, but what I wrote here was all the neighboring points have higher values. That's kind of changing which thing you're thinking about, but I think you understand what I mean. So that's local, and of course absolute is well, what happened with absolute extrema, absolute mins and maxes, is you usually were considering the function on a closed domain. So let's see, starting with an axis, we then draw, I think I actually still want to do like this. And a typical example would be something like a parabola. So something like that, say, so ending there. Then well, assuming that this was actually drawn symmetrically, then those 2 points would be absolute maxes, and then we have a local min that is also an absolute min there. And maybe this wasn't emphasized so much in Calc 1, but I'm going to emphasize it now. It's important that the interval in question was a closed interval, because if this was instead an open interval, uh, like, well, okay, maybe I'll make both of them open. An open interval has an issue because, um, in this case, the function never obtains the maximum. There's always a value that's closer to the um, this value here, where the function will be higher. So the problem is that because you're not including the endpoint itself, you can get arbitrarily close to the endpoint, and you can always kind of shrink that distance. So you're always able to produce successively larger values that will never actually reach the max that you can clearly see should be there. So for one of the statements that you learn about, which I sort of am jumping ahead to, one of the statements I have is that on a closed interval, the function always obtains its absolute mins and maxes, and that you know where they occur. So they always are, they occur either on critical points or on endpoints. Okay, let's come back to what we're doing here. So we should remember the definition of critical points, another term that was introduced. So a critical point, these are the places on the function where when you plug that point into the derivative, you get 0 or you get that the derivative is undefined there. So these critical points, and the process is that you normally, this is how I phrase it, you take the derivative, you set it equal to 0, and then you solve to figure out all of the critical points, find all the places where derivative can be equal to 0. And yeah, the whole reason that we do that process, that we look for critical points, is because we know that the local mins and maxes, the local extrema, occur at critical points. Um, mhm, absolute extremely. You also have to test the endpoints. Um, yes, and then after you find these critical points, then you have these tests that you can perform to determine what type of critical point it is. So you should remember the terms that the terms of local min, local max, and well, sometimes your critical point is neither a min nor max, in which case you just say that. So there was the first derivative test where you compared values around your critical point, and whether it was going from like plus to a minus or minus to a plus, that told you whether you had a min or max. That is not as that's not gonna be as useful for us in Calc 3. What will be useful is the second derivative test, where what you do is you take the second derivative of your function and then you plug in at the point. So that tested for concavity, which I didn't define here, but that's okay. So concavity is the second derivative, and when you evaluate the point, so if it's positive, that means you're concave up. Your function is opening upward, which I suppose I can just do a quick sketch of. So concave upward looks like that. Concave downward looks like that. Right. And so the property of the concavity tells you then whether your critical point is a local min or a local max. Okay, so the reason I'm bringing all this up, I'm refreshing all this Calc 1, is because we're going to basically generalize this to 2 dimensions. A lot of these statements, I think pretty much everything except for the first derivative test, there is an analogous version of, and we're going to go into that now. Okay, um, so here is the definition of critical point when we're dealing with a function of 2 variables. So the critical point is where we set the first derivative, but this time our derivative is the gradient. We set that gradient equal to 0, or it's undefined. So that's going to involve, and we'll see that in the examples below, that's going to involve solving a system of 2 equations. You'll have f sub x equal to 0 and f sub y equal to 0, and you'll solve for all possible coordinates x naught comma y naught that solves that system of equations. Okay, so you have this thing as well, Fermat's theorem, saying that the local mins and maxes, the local extrema, they occur at critical points, which is exactly analogous to the Calc 1 situation. Okay, right. We have one additional type of critical point introduced in 2 dimensions. So you notice that in the, how should I say this? In the x direction and in the y direction, this critical point here, on the positive z-axis, this actually has negative concavity in both directions. The local, and this is a local max, a local min is concave up in both the x and y directions. Yeah. Whereas with the saddle, you'll see that in the x direction, this is concave down, but in the y direction, this is concave up. So the fact that there's 2 different types of curvatures or concavities going on, this is going to be reflected in what is right below here, the second derivative test. So this is how, once we've discovered the critical points, we feed them into this expression to test the critical point. So this is the 2-dimensional version of the second derivative test. So you have this function called the discriminant, and it's comprised of the second order derivatives, so fxx, fyy, and fxy squared. You would do fxx times fyy, and then you subtract off fxy squared, evaluating all of them on the critical point that you're testing. Okay, and just as a side comment, this discriminant is sometimes called the Hessian determinant. So the Hessian is actually a matrix of second order derivatives. So it would just be this, but without the vertical bars. It would instead be with square brackets to indicate that it's a matrix. And if you take this determinant of this 2 by 2, you get indeed this expression, notice that this antidiagonal, these two terms are equal because of Clairaut's theorem, right? We can switch the order of the mixed partials. fxy is equal to fyx. These two are equal, and so that ends up giving you this this term there, or at least we assume it's equal, because in all nice circumstances, we deal with nice functions where indeed they are equal. Okay. Okay, so right, you compute this guy. This is going to give you back a number because a and b are numbers. You're just plugging a point into a function and you get back a number. How do we use this number? So, if the discriminant is positive, well, let's start with the negative. If the discriminant is negative, you know right away it's a saddle point. Okay. Effectively, you can think of this as saying that the two different curvatures, the two different concavities, when you multiply them together, they give you a negative number, meaning that the concavities are kind of opposite. If the discriminant is positive, then this breaks into two cases. It could be a local max or it could be a local min. So you need to do one further calculation. You need to evaluate the critical point on fxx. You could also choose fyy, it doesn't matter, but it's pretty much convention that people will use fxx. So what that's doing is, so the discriminant, when it's positive, it basically means that the x direction and the y direction have the same curvature or concavity. So, but that could be both positive or both negative, right? Like positive times positive equals positive, and negative times negative is equal to positive. So from that information alone, you can't distinguish it. So we need one additional test to see, is it concave up or concave down? That's what the second derivative in just the x direction does. Okay, so if it's greater than 0, then just as in the Calc 1 case, that indicates that we have a local minima. And if instead the second derivative is negative, then just as in the Calc 1 case, that means that we have a local maximum. And then finally, if the discriminant is equal to 0, that the test is inconclusive. You can't tell anything from that. You'd have to use some other technique in order to determine what type of critical point you're dealing with. Okay. Right, so now an example of how to classify critical points. Well, find them and classify them. So I purposely chose a problem that is harder than your homework, just because I think that the homework problems that were given, they're actually on the easier end. It's more standard to see problems that are a bit more involved. So, okay, how do we begin? Well, to find the critical points, we solve for when the gradient is equal to 0. Okay, which means that we need the first order derivatives. And then in order to test them, we're going to need the second order derivatives. So we may as well compute the first order derivatives and second order derivatives all to start with. So let's see. I'll talk through it since let's see. So the x derivative is going to give me 6xy minus 6x. Yep. And then the y derivative is going to give me 3x squared plus 3y squared minus 6y. And then, to take the second order derivatives, I take the x derivative of f sub x to give me f sub xx. That's going to be 6y minus 6 for that. The y derivative of this is going to be 6x, just 6x, yep. And then f sub yy, I take the y derivative of f sub y. That's going to give me 6y minus 6. Yeah. Okay, so those are all of the first and second order derivatives. Next, solving the critical points. So we take our first order derivatives, we set them to equal to 0, and we solve this system of equations. So this is where I specifically chose something that's a bit harder, right? It will end up depending like how complicated your system of equations is to solve. Sometimes that's simple, and sometimes it can get fairly complicated. In this case, this is sort of in the middle. All right, so the way I would start is noticing that I can factor a 6x out of the first equation, which will then give me this expression. And then saying that this is equal to 0 means that either this factor is equal to 0 or this factor is equal to 0. So either x is equal to 0 or y minus 1 is equal to 0, which would mean that y is equal to 1. So we end up with these two possible cases. So now we just try out these cases, and we feed them into the second equation in order to try to get one of the other conditions. So this this x equals 0 should give me a statement on y, and this y equals 1 should give me a statement about x. So let's see. If we let x equal to 0, we plug that into here, we end up with 3y squared minus 6y equals 0, which is right there. Well, okay, then I factor it. So I factor out a 3y, and I get this is equal to 0. And then that implies that y is equal to 0 or y is equal to 2. So that gives me 2 points right there. I get the point 0, 0 and 0, 2, which are these first two guys. Okay, missing some commas, but that's okay. And that was the first case, the case x equals 0. Now for the case y equals 1. So we plug that into here, and then we get 3x squared plus 3 minus 6 is equal to 0. I think I wrote that there, yep. And then simplifying and then factoring, we set this equal to 0 and solve. And so that gives me that x is equal to plus or minus 1. Okay, so that gives me 2 additional points. 1, 1 and minus 1, 1, which are these two. So in total, we've found 4 critical points for our original function. And the problem asks us to further classify each of these points. Right, so to classify, we use a discriminant. So we construct it by using these second order partial derivatives. So xx times yy minus xy squared. That's what you're supposed to do. You might need to memorize that. Well, sometimes it's given to you on the formula sheet, the formula for discriminant, but it's kind of easy to remember as well. So. Okay, so what you can see is that when we multiply these, so I factor out a 6. If you factor out a 6, you'll get a 6 times y minus 1, and then you're multiplying it by itself, so you're squaring it. That gives you 36, where is it? 36 y minus 1 quantity squared. And then fxy squared is just going to be 36x squared. So you get that guy. Yeah. And then plug all the points into the discriminant to test things out. So you see that I do the calculation there. Well, I'm not showing you the work, I'm just giving you the end result. So you just plug it in and you get some numbers out, and that'll tell you some things. With 1, 1 and minus 1, 1, you can tell right away that these are saddle points. But with these two, because it's greater than 0, you need to do one further test with just f sub xx, which was 6 times y, well, 6 times the quantity y minus 1. Right, so in this case, yeah, this gives you minus 6, this gives you plus 6. That's funny. I know what I meant to write. I meant to write that that's less than 0. I also meant to write comma and comma. That's not so important. But okay. Right, so just to, make sure you're paying attention, this means that this point is so it's decreasing, concave down, so it's a minimum, or maximum, sorry, it's a maximum, whereas this guy is concave up, so it's a minimum, right? That's what it should mean. So 0, 0 is supposed to be a max. Where did I write that? Yeah, max, okay, there we go. Yeah. All right, so 0, 0 is a local max, 0, 2 is a local min, and 1, 1 and minus 1, 1 are saddle points. And I've inserted a graph of that, and you can play around with the graph on this link if you want to. So you can clearly see, maybe I will pull it up. I have it somewhere. Yeah. So it's pretty clear to see the local min and max, but it's a little bit harder to spot what's going on with what's going on with, how do I zoom in? declares to be the saddle points. That's the part that's a bit harder to focus on, but it's these weird node areas. Yeah, it's where there's like this very strange line, but that's where the saddle points are on this guy. It's harder to see in the graph here. Okay, let's continue. Right. So now we generalize this other type of problem where back in Calc 1 you had given a function and given a closed interval, find its absolute mins and maxes. And you'll remember that the process to do that was you find the critical points and then you test the critical points and test the boundary points. You just plug them into the function and then you just read off what is the min value, what is the max value. Those would be the mins and maxes, the absolute mins and maxes of your function. There's a similar thing going on in Calc 3 with functions of two variables. First, a fairly important statement, a theorem, in fact, extreme value theorem. It says that as long as you're talking about the function on a closed and bounded domain, so closed means that it contains all of its boundary points. So you don't have that odd situation of like an open interval or a half open interval. Those are not allowed. Okay, those are not closed. A closed interval is this guy in Calc 1. But closed intervals can be much more complicated in Calc 3 because we're talking about subsets of R2. So you may encounter a disk as being a closed interval where it contains the boundary circle rather than, if I stick to my color convention right now, instead of this open disk where I don't include the boundary. A problem that you do have is that you have a rectangle with boundary, and so that is closed and bounded. So, okay, I mentioned closed. Closed means that it contains the boundary points. Bounded means that it's finite in all directions, right? There's not a particular direction in your domain, in your set, where you can extend off to infinity in some direction. So that's what it means to be bounded, is that it doesn't extend off to infinity, your set. Okay, so as long as the domain that you're considering the function over is closed and bounded, then this theorem allows you to conclude that the function must attain its absolute min value and max value on that set. Okay, so that means that the absolute min and absolute max always exist. This is very much similar to the Calc 1 situation. So I'm emphasizing this because it's often the case when I've taught Calc 1 where students will claim that the absolute min or absolute max doesn't exist, but the problem is over a closed interval, and so it must exist. It's a theorem. It must exist. So it's that their answer is immediately wrong. So don't make that kind of mistake, right? If your domain is closed and bounded, you know right away the function definitely attains its absolute min and absolute max on that domain, and so it's not a question of whether or not it exists. It's a question of finding it. Okay, and how do we find it? So, well, where can these absolute mins and absolute maxes occur? Well, first of all, they can occur on critical points of your function. So that's going to involve what we just discussed, the process of finding the critical points. You take you set the gradient equal to 0 and you solve. Right, that process we did above. But there's more than that. In Calc, so remember in Calc 1, you didn't just have to test like the critical points. You also had to test the endpoints. And the analogous version of that is you have to test the boundary points of your domain in Calc 3. So the boundary points of a disk would be this circle that bounds the disk. And for a rectangle, it would be the four sides, okay, which shows up in one of your problems, and it shows up in one of the examples that I'm doing. Okay, so we have to test, we have to find critical points using the gradient, and we have to also test on the boundary. Now, one comment that I make here is that when we restrict ourselves to the boundary, we're actually lowering the problem's dimension down by 1. We're bringing it down to a problem in dimension 1. You can see like that this line segment, right? If I restrict to it, it's a line. So you can then sort of treat your function as a function of one variable, which then brings you back to the domain of Calc 1, where you would use the critical points along that line, and then you'd also test on the endpoints. And so that is what you're going to see happen with this example. This example is defined over a rectangle. The domain has x range from 0 to 4, y range from 0 to 2, and we have this function. Okay, so first of all, we find the critical points, and then we're going to deal with the boundary. So the boundary is always going to be the painful process. Well, for rectangles, it's fairly painful. For triangles, it's slightly less, because there's only 3 sides in that case. One of the sides tends to be annoying. For circles, well, usually with circles, you'd be given a nicer function. Unfortunately, the textbook decided to do a really terrible function, or they did something kind of bad, and so the calculation ends up being messy, and I copied that down as well. I should also mention that this example is copied from the book. I forgot to write that here. Anyway, okay. So first, we're finding the critical points. So we're setting the gradient equal to 0, and we're solving. So f sub x would be 2x minus 2y minus 4, and fy is going to be minus 2x plus 8y minus 2. Okay. Right. And let's see. Then we set them equal to 0 and we solve. So I'm bringing the 4 over to the other side, dividing by 2. Is that what I'm doing? Kind of. I mean, it might be easier to see this as just dividing everything by 2 first, and then moving the y to the other side. So that's going to give you x minus 2. Yeah, okay. And then next, I believe I plug this into this equation. So I plug y equals x minus 2. I replace the y here with x minus 2 in parentheses. So you get 8x minus 2x, which gives you 6x. And then you get a minus 16 minus 2. Okay, yeah, which I wrote there. Okay, and then that's a total of minus 18. Bring it to the other side, divide by 6, you get x equals 3. Yeah. Okay, so with x equals 3, you then plug it back into here, and you get y is equal to 1. So that gives you that this function only has one critical point. Well, what you might call it an interior critical point. So the boundary may also contain critical points, and that's sort of an artifact of how you slice your domain up. So just because we did this calculation and we only found one critical point doesn't mean that that's the only critical point that exists. There are boundary critical points that are not detected through this process, that you have to actually do things using the boundary. So this only finds this interior critical point of 3, 1, and then I plug it in right away just to kind of keep things clean, I guess, in my work. All right, next, the boundary critical points. So we have 4 sides to this rectangle, labeled L1 through L4. And for each of these sides, what you do is you basically you reduce it to the Calc 1 problem. So let's see, for L1, notice that we vary in the x direction, but our y coordinate is constantly 0. So this is basically plugging in t comma 0 into the function f that you're given, and where t ranges from 0 to 4, because you want the x value to range from 0 to 4. And then when you actually plug it in, so I'm legit looking at this expression, and I'm just plugging in y equals 0 in this case, and that's going to make a few of the terms disappear, and you just end up with this. And so now this is the function on the line L1. So we end up reducing our function because we end up restricting ourselves to just a single line. Okay, and so that's why this reduces to a Calc 1 problem. We end up having a function of one variable on a closed interval, and we're trying to find absolute mins and maxes. Well, really, we're trying to find critical points on the line, and then we will also have to remember to plug in on the boundary of the line, which are going to actually just be the vertices of the rectangle. So each of these four lines is going to have two endpoints, and well, they're going to be some in common with each other since the lines meet each other. But anyway, so continuing, let's see. You have gamma 1, which I'm using to describe the path along the line segment L1, taking its derivative, that should be pretty clear, solving for the critical point, you get t is equal to 2. So that corresponds, I sort of look at what I'm doing up here, that corresponds to the point 2 comma 0 for the way that we've parameterized this line segment. So 2 comma 0 is a critical point, a boundary critical point. Okay, and then we plug that in. Fine. Along L2, let's look at that. So L2, the x-coordinate is constantly 4. The y-coordinate varies from 0 to 2. And so that's what we have here. The x-coordinate is 4. The y-coordinate varies from 0 to 2. When you plug it into the function f above, the terms, some terms disappear. You're left with this. Take the derivative, set equal to 0, and solve. You get t is equal to 5/4. And so that gives you the boundary critical point, 4 comma 5/4. I don't think I actually checked that all these points lie inside. They should lie inside. That's something that you should check to make sure that the whatever points that you find, that they are in the domain. If they're not in the domain, then you can exclude them. Okay, so you get this point, then you plug it into f, you get a number. We're going to compare all these numbers at the end. Along the third line, let's see, x varies from 0 to 4, and y is constantly 2. So we have this substitution. We substitute into the function f. We get this function of one variable, take its derivative, set equal to 0, solve, get t equals 4, plug it back, well, okay, so you get the point 4 comma 2, you plug it in, you get 20. Okay. Okay. And then along L4, let's take a look again. So L4, the x-coordinate is always 0, the y-coordinate goes from 0 to 2, which gives you this statement. And then you get this when you actually plug in, simplify. Then you take its derivative, set equal to 0 and solve, you get t is equal to 1/4. Plugging this point into f, you get this value. Okay, and then lastly, as I said, you also need to test on all of the corners of your rectangle. So think of that as the boundaries of the boundaries, right? The original boundaries we're talking about were the lines, the edges, and then the boundaries of those would be the vertices of the or the endpoints of the intervals. And so you end up getting 4 vertices, and you have to test all of those as well, because it could occur there and not be detected through checking along the edges. So that's a somewhat involved process. You have a lot of calculation going on here. So after we've tested all that, then we kind of look through all of our values. It would have been nicer if I had gathered all of it together. Maybe I'll just underline all of the values. So we got 20, we got 20, we got 23, we have these 4, okay. And I think there's a few more, yes. So we had this value here. We had this value there. 1, 2, 3, 4, yeah. So when you look through all of these, then you'll see that the maximum value you got was 36, occurring at 0, 2, and the minimum value that was obtained was 17 at 3, 1. This was the interior critical point, way back at the top, I guess. Yes. Right, and well, the important part of this was actually the value. You don't really need to specify where it occurs. I just happened to write it because the book does as well. So this was what you were after, finding the absolute max value and absolute min value on the domain specified. It's this somewhat lengthy process. Okay, you get these values. Right, and your problem is very much similar to this because it's a rectangle as well. And yes, here's a picture depicting this. So you can see that we actually have the maximum occur at the vertex. And I believe if you didn't test the vertex, you wouldn't have spotted it. So that is that's one of the reasons why it's necessary. It's all about how you clipped this function, how you yeah, how you ended up like clipping the domain that you're considering. So if you were to extend this further that way or that way, this point would the maximum would shift alongside it because you can kind of tell that the function is increasing in this direction always. So the fact that this is an absolute max is an artifact of how we set up the bounds of the domain that we're considering. Local min here makes sense. Global min there. Okay, that's a bit more proper. And then local minimum there. This is also, it looks like it's an artifact of how we clipped it. You can see it's also on the it's also on the vertex. Yeah. So yeah, just this visual way of thinking about it hopefully is convincing and shows you that you actually need to test everything. You need to after doing the first derivative test, you have to test for critical points along the boundary, and then you have to test the boundary points of the boundary, the vertices, really, the endpoints of the interval. Right, a lot of testing. Okay, and then this example. So this one is a circle. You can see that the domain here is defined to be a circle of radius 4. Well, a disk, right? This less than equals means that we include the interior. We include, for example, the origin 0, 0. So this is a disk of radius 4. Okay, and this is a function we're trying to find the absolute extrema for. So, right, the way we start the process is we set the gradient equal to 0 and solve. Right, so the first derivatives, we calculate them. That's pretty straightforward. 2x plus 4 for the x derivative, 2y minus 6 for the y derivative. Setting them equal to 0 and solving. So this is straightforward, right? Much easier than the very first example that I gave, where you ended up getting 4 points. So this just gives you a single point, minus 2 comma 3. Plug it into the function g given, get minus 13. Maybe I'll underline that because we're going to have to compare things later. Although we don't need to compare as many things. Okay, so just like in this example, we parameterized the boundary, but in this case we had 4 different pieces to parameterize, since each of these parts is not, you can't combine them into a single function. You can't like parameterize L2 and L3 as a single function because of the fact that there's like a corner there. It doesn't smoothly go around. But with a circle, you can parameterize the entire boundary with just a single function, right? So if you use cosine and sine, and we scale it up to be of the correct radius by multiplying both by 4, and then in this way, with cosine as x and sine as y, we end up doing counterclockwise parameterization. It doesn't matter if we're doing counterclockwise or clockwise, at least not right now. It might matter in a next two in the last chapter of this course. It might matter, but for now it doesn't. And t runs from 0 to 2 pi just to completely go around the circle. Okay. So now with this parameterization, you can then plug into g of x and y, and then view that as a function of one variable, which I'm again calling gamma. Gamma is a rather common letter to use to denote like a path in mathematics. So I just sort of reached for gamma, and used it as a letter. Okay, so this is our parameterization. We end up plugging in, right? Plugging x and y in, as you can see. And then simplifying, you end up with this guy. So you see that these two, sine squared and cosine squared, will combine. There's a 16 in front of both of them, so you end up with 16 here. Right, 16 times 1. And then these guys are just those. And so that is our function that is the function restricted to the boundary. The function restricted to the boundary just looks like this function of one variable. And we're now in the situation where we're trying to find the critical points for this function of one variable on a closed domain. Now, technically, it's not closed because 2 pi and 0 are identified with one another. They're the same point. They're this point right here at 4, 0. So it's closed, but in a different sense. Well, I'm not going to explain that. But so we take the derivative, we set equal to 0, and we solve. Okay, and then this is where it gets a little bit bad. So moving this to the other side, and then you divide the cosine, you divide the negative 16 over, and you get tangent of t is equal to negative 3 over 2. Now, the fact that it's like this is bad, I think, I find. So for a function that is kind of easier to work with, you'd somehow have like this g function, be able to cancel things out nicely to the point that this derivative is not as terrible to work with. Unfortunately, the book gave you this, and so the way that this worked is that you are solving a trig identity over an interval, t going from 0 to 2 pi. This has two solutions. You can kind of think about what happens on the unit circle. Well, tangent being negative is somewhere on these two quadrants. And, well, where exactly it is a bit harder to specify. You'll have opposite side being 3, so it's like 3 up here and 2 down here is going to be that point. So we're talking about like a ratio of sides. And then there's a similar thing going on over here, negative 3 and 2. My sketch is going to be a little hard to read when I upload this. But yes, you end up with these triangles that end up giving you the expression tangent of t is equal to negative 3 over 2. So there are corresponding triangles to this trig identity. And so that ends up giving you these angles. So it's pi minus arctan of 3/2 and 2 pi minus arctan of 3/2. So and then you end up, well, at least the book ends up just using some trig identities to actually evaluate this. So notice that because this equation has two solutions, we have two different cases. We have two different possible values for t, as you can see by the picture. So there's t being this angle, t being that angle. If t is this angle, then let's see. What we're trying to do is we're trying to relate this back to g. We're trying to plug it back into g, which requires us to know sine and cosine at t, which is why we do this calculation. And then there's some trig identities going on here. Being able to get rid of this pi minus, this is a supplementary angle. So doing pi minus something is reflecting it across the y-axis. And so when you're reflecting an angle across the y-axis like this, the sine function gives you the same value because sine is the y component, or yeah, the y coordinate. So the sine doesn't change in sine. The function sine it remains positive. And then for cosine, well, the cosine does change because cosine is this is the x coordinate. So the cosine, the x coordinate is going to be negated when you consider the complementary angle. So that was the first equality. The next thing is then considering the triangle corresponding to arctan of 3/2. So arctan of 3/2 is this angle, whatever the angle is, numerically. it sets up for you a right triangle, opposite side 3, adjacent side 2, and then the hypotenuse is of length 9 plus 4, which is 13 square root. Then when you read off the value of sine, you're going to get opposite over hypotenuse, 3 over root 13, which if you choose to rationalize the denominator, you get this. For cosine, adjacent over hypotenuse, 2 over root 13, rationalizing the denominator gives you this. Okay. And so this was sine and cosine, but in order to plug into the parameterization to get back to x and y, you multiply by 4. So the x comma y is this, which gives you this coordinate. When you plug this coordinate into g, I'm suppressing all of the calculation. The book actually tries to express it, which is, I don't know. It looks annoying if you were to do it by hand. But you get this expression, and then you can plug it into a calculator to get a numerical approximation of it. And then you have to do the whole thing for this other value t. I think the process is pretty similar. So, well, okay, the one thing is 2 pi reflects differently, I believe. I didn't think about it, but yes, I believe 2 pi has to reflect it about the y-axis. So if we're in this situation, then it's about 2 pi all the way and then minus. So yeah, so 2 pi minus arctan of 3/2 is some angle that looks like this in the 4th quadrant, and then you're reflecting it to get up here into the 1st quadrant. So you've ended up flipping the y coordinate, which corresponds to sine. That's why it's a negative there. And then the cosine is the x coordinate. Yes, the x coordinate, which stays the same. So there's no sign flip there. And yeah, same triangle considerations will give you those values. Convert it back to be x comma y, plug it into g, do some painful algebra, and you get a number. Okay. And then considering what is the smallest value that you see, what is the biggest value you see, I suppose I should underline such values so that we can more easily kind of scroll through and look at them. Where's the other one? There. Yeah. Okay, so yeah, minus 13, minus 12, and 44. Yeah. So minus 13, and then this 44, which is exactly 16 plus 8 root 13. Those are the min value and max value for this function. And I have a little plot here, so just as a comment, if you're reading the book, you'll be confused because actually the web version, for some reason, its graph is wrong. The coordinates are labeled completely incorrectly. So yeah, that's the corrected version. And I guess that's it.